let's just start here. Probably start at like 3:05 or 3:10 or so.
Good plan.
Putting in a request for a dark mode.
For the GIMP.
Yeah.
I genuinely don't know how to do that. Is the issue.
So you see the black and white thing?
Yeah.
There. You just swap those. Now the is the background, and then white is the foreground, and so now you can. So I mean, you can fill the whole background with black first, and then just swap them.
Sure.
Or if you start erasing with that, it'll make it all black.
Oh, perfect.
There you go. Yeah.
That's good. Yeah.
Yeah. Nice.
Dark mode at home.
Yeah, I downloaded this program like actually an hour ago.
Oh, good
This will be
luck.
exciting then.
I used to
There's
just do this in MS
also,
Paint, but I figured I should be slightly more professional. Drawing tablet's working. Okay.
Excellent.
There's the
You got a drawing
Discord
tablet.
whiteboard.
Let's go.
Pokemon X were very loud.
Sorry.
That's right. You could also use Krita. Krita is my recommendation because GIMP is
It's fine for this
difficult.
purpose.
Yeah. For now, don't worry about it.
Okay. 2 more minutes.
All right.
How long do you think it'll last?
I have no idea. Genuinely.
Good to know.
It depends on how long I think I need to take on things and how many questions there are, I suppose.
Approximately 15 seconds.
Yeah. So I'll just talk really fast. And if you can't keep up, that's on you. I'll teach you all of group theory in 4 picoseconds. Okay, I think it's as good a time as any.
Mm-hmm.
All right. Let me just make sure. Okay, this is group theory 101. I don't know. I'm going to cut the video here, I suppose. Okay, so let's start off with set theory, because groups are, I'm not really assuming any prerequisite knowledge here, and groups are sort of built on top of sets, so it's important to know some facts about sets, what they are, what you can do with them. So let's start off with what is a set. Set is a collection of things. No order. So I'll give an example in a second. And no repeats. So, for instance, this is a set, right? This is a set. This is a set. This is the set containing nothing, which is allowed. It doesn't have to contain anything. We call this the empty set, and we denote it like this. And importantly, this is the same as this. These are the same set. We will encounter later objects that are like sets, but we care about order. But for now, we're just dealing with sets, and sets don't care about order. Additionally, this is not really a set. You could say this is actually just the set containing one element, but because this is really annoying and bad notation, we just won't consider this a set. Okay. So, some common sets that we'll work with here should be very familiar to anyone with any sort of math background. The naturals, which I'm bad at math building, but it's like that, I think, which is 0. I think I did the math build wrong. Whatever. It's like this, I think, actually. This is the set 0. We'll consider 0 a natural for this. 0, 1, 2, and so on, right? The integers should also be very familiar. It's just 0, -1, so on, and then also 1, and so on. The rationals, which are, all the rationals I can give. I'm going to use what's called set constructor notation, which I'll explain in a second. So I should, okay, I think I skipped a bit of notation. If I say 1, this symbol means in, this one right here. If I say 1 is in a set S, that means that 1 is an element of it. This should be, fairly intuitive. So for instance, 1 is in this set, and 1 is not in this set. And it should be clear that no matter what A I choose, this is always false. There's no A in the empty set. This notation basically means that we iterate over all P and Q in the integers, and we divide them. And I should also clarify Q not equal to 0. So the rationals, which should be familiar, are just any fraction of integers, right? Notice that here we do get repeats, and that's okay. We just only count the repeats once. For instance, if P is 2 and Q is 4, we get the same as if P is 1 and Q is 2. But this is all sort of unnecessary. Intuitively, the rationals are just any number that's expressed as a fraction of integers. Lastly, the reals, which are kind of hard to construct rigorously. So I'm just sort of going to work with the intuition that people have. They're all the numbers we typically work with that aren't complex numbers. It's not really worth the time to rigorously construct them. Okay. So let's talk about some things we can do with sets. Let's Control-C here. So I'm going to define a few sets first to work with, just small sets. Let's take 1, 2, 4, and call this set A. And let's say 3, 5, 6, 4, 2, 9 is B. So just integers for now, naturals even. Okay, so a few things we can do with these sets. We can make new sets from these sets. So the first one we'll look at is A union B, which is anything that's in A or B or both. So in this case, it would be 1, because that's an A, 2, because that's an A and B, 3, because that's in B, 4, because that's an A and B, 5, because it's in B, 6, because it's in B, and 9, because it's in B. So we get a set that contains A and B inside of it. We also have A intersection B, which is sort of analogous. It's sort of a stricter operation. We, instead of taking things that are in either B or A or both, we take only things that are in both A or B. Just a note, if you're familiar with symbolic logic, you'll notice that these are the symbols or and just like curved off. That's intentional, obviously, because this is kind of analogous to or, and this is analogous to and. So this, for instance, would be the set 2, 4, because those are the only elements that are in both A and B. This is something you can write. This is not a new set. This is a statement, and it's either true or false. What this means is that A is a subset of B if, for any element A in A, it also follows that A is in B. So no matter which element of A we choose, it's also in B, which should be intuitive as the idea that every like A is contained as a part of B. In this case, A is not a subset of B because 1 is in A and 1 is not in B. But if I remove 1 from A for a second, then it does follow that A is a subset of B. Now, it should be clear, these are just a couple set theory properties to test your intuition. It should be clear that A intersection B is in fact a subset of A and a subset of B, and that A is a subset of A union B. But I won't prove these.
I think A... Oh, sorry.
Sorry, if you have a question, please ask.
Never mind.
Okay. And yeah, if anyone has a question, just feel free to unmute yourself and interrupt me. Okay. Okay, a couple more operations that are a bit more complicated. This will be B complement A. What this means is all the terms that are in B, not in A. So, for instance, in this one, it would be the terms 9, 6, 5, 3. Because 1 isn't in B, so it doesn't meet the criterion, and 4 and 2 are in B, but they're not in, but they are in A, which also doesn't meet the criteria. So in this case, B complement A is going to be 3, 5, 6, 9. This does, you can see clearly this does work when A is not a subset of B, but typically when we use this operation, we're going to be considering A as a subset of B, but not always. So I'll draw a little Venn diagram just to finalize this notion. If we have, just erase these. Okay, if we have a notion of sets as these sort of boxes, right, where anything that's in this big circle is in B, and anything that's in this big circle is in A, right? Then we can label, and then say we have this big, yeah. So A intersection B is going to be this little guy in the middle. A union B is going to be this whole thing, the whole Venn diagram, not anything outside here, but everything in here. So I don't really know how best to denote this, but all of this is AUB. And then B complement A is just this section. Okay. This does help get some intuition. For instance, it is a fact that you can pretty easily prove that B intersection A, I might say, sorry, B complement A union A intersection B is in fact equal to B, and that this is always true. You can do this by just running through the logic. I might say cap at some point for A intersection B because that's the latex and it's easier to say than intersection, so if I say cap, that's what I mean. Okay. In this case, A is a subset of B if and only if this is empty. And so in that case, the Venn diagram would really look more like this, A and B. Okay, anyways, that's, I think, enough with that. Oh, I should mention, lastly, two sets are called disjoint. What did I do? Oh, I changed my color. Okay. Two sets are called disjoint if A intersection B is the empty set. So there's nothing in both of them, which should make sense. And again, it also follows these two sets up here. These are disjoint in all cases. Anyways, okay. There's, I think, one more operation. Let me check my notes. Yeah, there's one more operation I need to go over, but I will go over it later, and let's talk about functions. So a function is a, again, this should be something that anyone with math background is familiar with, but I will give a more rigorous foundation. A function maps from a set A to a set B. We'll write it like this. This is called the this is called the domain. This is called the codomain. And every element A in A gets a unique element in B called f of A according to f. So we can put any element of A through F and get an element in B. What I mean by unique is that there aren't two elements called F of A that are not equal. So you might have heard that called a relation. This is basically the vertical line test if you're dealing with the real numbers. But we can have that B is not equal to A, just to be clear, and F of B equals F of A. F of A is not the only thing, A is not the only thing that maps to F of A in general. Okay, so for instance, just a couple examples here. If we're dealing with our sets A and B from earlier, we could define a function. We can just write down the function, and since we have finitely many elements, by just telling the function where to bring everything. So let's say 1 goes to, this means goes to, maps to. Let's say 1 goes to 5, and we say 2 goes to 3. And let's say 4 goes to also 5, for instance. Okay, so this is a function. We've assigned every element in the domain at one element in the codomain. And we can look at the properties of functions. But first, just a note, most functions you define, it's cumbersome to do this unless the sets are small, and it's impossible if they're not finite, because obviously you can't write down infinitely many. It's impossible if the domain is not finite, because you can't write down an infinitely long list. So in this case, we would write something like a rule, right? So for instance, I'm sure this is a familiar function on the reals. F from the reals to the reals. This should be familiar. Obviously, the rule is just every element in the domain gets taken to one element in the codomain, which is just x squared. Okay. Anyways, let's talk about some properties of functions. There are two big properties here called injectivity and surjectivity that will come up a lot. So injectivity is if we have A and B in the codomain, or in the domain rather, keep mixing them up. Then F of A, then with A not equal to B, I should mention. When I write down two letters, usually it's implied they're not the same thing, but I'm going to explicitly say it either way. Okay, with A not equal to B, this means that always F of A is not equal to F of B. So what this means is that the only way to get to F of A through F is to put A through F. We can't put something else through F and get to it. So if we imagine this, here's another visualization of functions. Say we have, these are our three elements of A. Say this is 1, this is 2, this is 4. And these are 6 elements of B. 3, 4, 5, I missed one. 2, 3, 4, 5, 6, 9. We can just draw one line from each dot here to the thing it goes to. So in our case, it would be this goes here, and this goes here. Injectivity, therefore, is that we have no dot here that has 2 lines going to it. The sort of other property that we care about that is, in some ways, it's not the opposite because they often go together, but it's sort of like a complement. I'm sure there's some category theoretical reason why this is rigorous. But surjectivity means that for every element in the codomain, so every element of this set, there's some element of the domain with F of A equals B. So every element in the codomain gets mapped to. So in this case, I should mention, our function here is clearly non-injective. But if I make this, say, 2, then it is injective. Our function here is not surjective, obviously, because 2, 4, 6, and 9 have nothing mapping to them. So surjective means every dot here has at least one arrow going to it. So it's clear, it should be clear that functions can be non-injective and non-surjective. They can be injective and surjective, which actually I should mention this. We call this bijective. When a function is injective and surjective. And they can be injective and non-surjective, and also surjective and non-injective. All 4 combinations are possible. Okay, so if we have finite sets, I might just actually, does everyone have this? I might just erase it to get more space.
You can make a new page too.
That's true. I don't know how to do that, but hang on.
File new, I think.
Okay, sure.
We'll open the new tab. Might have to fill it with black again. Oh no, it's smart. Okay.
Okay, sure. So if we have A and B are finite, for now, let's assume they're finite. any finite set. We're not using our A and B from last time. And let's say that A, this means the size of A. I'm only going to use it when A is a finite set. I'm not going to try to generalize it. We don't need that for this. There is a generalization. I'm sure many of you are familiar with it, but this just means the number of elements in A and B. So in this case, we're saying A and B have the same number of elements. I'm going to state a theorem. I'm not going to prove it, but I think it should be intuitive. So say F from A to B is injective, then it is surjective. And vice versa. This, I don't know how to spell. Sure. So intuitively, this, if we draw a graph, say they both have 4 elements, right? Like this. Intuitively, if we draw one here, well, we only have 3 options left to draw this one too, because we can't draw it to that one. So say we put it, here. We have 2 options left here, so we put it up here, and then this one goes here. Because each one of them went to a different one, and there's 4 of them and 4 of them, it should make sense that this is always going to catch all of these. Okay, it should also make sense. So let me write this down. Say we have A and B are finite with not the same number of elements. If you remember, bijection is an injective surjection. So a map that is injective and surjective. It should be clear that you can't have a bijection between these 2 sets, because you can't have a surjection even. How would you get to 5 elements from 4 elements? And if in the other case, the second one is actually smaller, how would we have an injection? Because we're going to map 1 to 1, 1 to 1, 1 to 1. This one can't go anywhere. So if the second set is smaller, no injections are possible. If the second set is bigger, no surjections are possible. So the bijection is only possible when they have exactly the same number of elements. That's just something useful to know for later. Okay, moving on from functions. Let's talk about... oh, I should mention, if you're familiar with like graphing real functions, injectivity is the horizontal line test. Anyways. Oh, also, if we have a bijective function, f from a to b, there is always some function f inverse from b to a, with f inverse of f of a is a, and f of f inverse of b is b. These are always true. So, it's the inverse function. You know what an inverse function is. I should introduce one more piece of notation. Say we have a function g going from some set A to some set B, and a function h going from some set B to some set C. We can define a new function, h of g, which is going to be a new function defined from A to C by just h of g of A is defined as h of g of A. So we just, to get A from A to C, we just pass it through G first to B, and then through H to C. Okay, so what's next? Let's see. Right. We also need to talk about preimages and images. So remember subsets from earlier. If we have, let's say we have a set C that is a subset of A, so it has only elements from A. We can define the image of C to be, we take the set of all f of C. And so, again, this is the sort of set builder notation I briefly glossed over earlier, but I'll give a picture to tell the idea. Say we have these 2 sets. Let me draw better dots. So you have these 2 sets, and we have like this function, right? And let's say this set of these 2 is called C. Then the image of C is just these 2. It's the things that elements of C map to, collected as a set. Of course, this statement isn't always true. For instance, if this is our set A, the image of A, the image of the codomain, is just these 3 here. In fact, whoops, I don't know what just happened. So this image of the whole codomain, or the whole domain, obviously is a subset of the codomain. We call that range of f, or image of f. And it should be clear from our definitions that a function f is surjective if this is true, if the image of the domain is the codomain. Okay, the preimage is defined similarly, and the notation here can be a bit confusing. But let's say, I gotta do some stuff. I'll redraw that picture in a second. Yeah, so say we have a subset C of the set B, then we call the preimage of C. Notice we're in the codomain here, not the domain. The preimage of C is the elements of A. Let's call them A. That map into C. So again, I'll draw another picture just to make sure this is intuitive. Different function this time. Let's say we take these two, or even these three is our subset of B. Then the preimage of these three is these two. Whoops. Okay, and that should be clear from our definition over here. Okay. The reason this is F inverse, it's actually not technically, well, it is related to the inverse, but this notion, the notion of F inverse as a function only makes sense when F is a bijection. This notion of a preimage always makes sense. The reason it's written this way is that when we do have a bijection, the preimage of something in the codomain is the same notion as the image of something in the codomain under the inverse function, which should be clear. Okay, this is good. Oh, I should mention a set is called a singleton if it has only one element. That's just sort of common term. So we can give a new phrasing over our definitions of injectivity and surjectivity. A function is injective if the preimage of a singleton is either empty or a singleton. Let's call it C. I should write B here. Sorry. So this is always going to be empty or a singleton. Because if this was more than a singleton, we'd have two elements mapping to B, which would be a problem. And surjection, similarly, is that the preimage of some element is never the empty set. It's always one or more elements. And so you can see how these intersect nicely. One of them says it's at most one of them says it's at least one. So when we have a bijection, we just have F inverse of a singleton is always a singleton. Okay, I think that's all I had written about functions. Let's define direct products or Cartesian products of sets, which is not too bad. So if we have, I'm going to give an example just to be nice. Let's say we have from earlier, we have A equals 1, 2, and B equals 3, 4. Okay. So we're going to write another way to form a bigger set called A times B. And this is defined as the tuples. Let me describe what a tuple is in a second once I finish writing this. Okay, so a tuple is kind of like a set, except, let me go back to my original page. So a tuple is still a collection of things, but neither of these are true. We can have repeats in tuples, and we care about order. So, for instance, some tuples would be, 3, 4, which is not equal to 4, 3. And of course, like 2, 2 is fine. Coordinates, for instance, are the primary example of tuples in like common math, which is related to this, and I'll explain that in a second. Here, A times B for a set A and a set B is the set of all tuples where the first element is from A and the second element is from B. So in this case, our set consists of 4 elements: 1, 3, 1, 4, 2, 3, and 2, 4. So a couple of facts about this. It should be clear if you know any like combinatorics that the size of A, if A and B are finite sets, the size of A times B is the size of A times the size of B, which of course in our case is true. A is 2, B is 2. There's 4 of these. Also, another important fact. This also makes sense because if you take A times the empty set, it's always the empty set, because we can't form any tuples because there's nothing to put in the second term. Another fun fact about this, if we take the reals times the reals, it should make sense that we get R squared, which this is clearly R squared. We have tuples where the first element's from the reals, the second element's from the reals. These are just coordinates in R squared. And of course, R to the n for finite n is just this. Okay, I think we now do equivalence relations. So I'll make a new page for this. So this is where we're starting to get some structure. Okay. I think we're good. Okay, so a equivalence relation, if we have a set A, equivalence relation on A, equivalence relation on A. Well, what's a relation on A? Actually, that's better. That's better. What is a relation on A? And then we'll specialize to equivalence relations. A relation on A is a way of taking any two elements in A, call them A1 and A2, and telling us if they are related or not. So we just define some rule. So say we define our rule. Let me just give a quick example. Let's say we define the integers, right? And our rule is A1 is related to A2 if A2 is equal to A1 plus 2, right? So here, for instance, 3 is related to 5. That's a true statement. 5 is related to 7. And 9 is not related to 9. And 1 is not related to 17. So a fun fact, which is, I don't think, too hard, every function from A to A is just a specialized form of a relation. We just associate, we say, once we have a function constructed, there's the relation A1 is equivalent to A2 if f of A1 equals A2. So it's a relation with some special rules, but that's just an aside. That's not too important. You can also just think about them as we did earlier. So some properties of relations that we might care about. Let's talk about 3 of them. They're the 3 big ones. Reflexivity. So this means that A is always related to A. So A is always related to itself, right? So in our case here, this is not reflexive because 9 is not it's not related to 9, and no number is related to itself. But all we need is that at least 1 is not related to itself to show that it's not true. Symmetricity, I guess, symmetry. I don't know why I made a new word. Is that if A is equivalent to B, or sorry, related to B, then B is related to A. So again, this is not symmetric because 3 is related to 5, but 5 is not related to 3. I could, however, define a different relation on Z that is A1 is related to A2 if A1 minus 2 equals A2, or A1 plus 2 equals A2. So it's sort of the symmetric version of this where 5 is actually related to 3 under this one, and 3 is related to 5. And this is symmetric. It's still not reflexive, but it is symmetric. The last thing we want is transitivity. This is if A is related to B and B is related to C, then A is related to C. So again, neither of these here is transitive because 3 is related to 5, 5 is related to 7, but 3 is not related to 7. And same thing holds here, that 3 is still not related to 7. I keep drawing 7s wrong. Okay, so we call, I should give an example. If we take Z and we take the relation on it that's less than or equal to, so A related to B if A is less than or equal to B, this is reflexive because A is always less than or equal to A. And it's transitive because if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. It's not symmetric though, clearly. It's like, 1 is less than or equal. Whoops. Change the color again. Because like clearly 1 is less than or equal to 2, but 2 is not less than or equal to 1. I missed. Okay, so we call something an equivalence relation if all 3 of these hold. And the logic behind this is that these are 3 things that hold about equality. Obviously, A is always equal to A. If A is equal to B, B is equal to A. And if A equals B, B equals C, then A equals C. And these are sort of really important properties about equality. Okay, so none of these are equivalence relations. This one fails to be any of them. This one is not reflexive and it's not transitive. This one is reflexive and symmetric, but it's not transitive. But, well, like I just said, equality is always an equivalence relation, clearly. But another example that will come up in just a second that a lot of people, whoops, should probably just erase things. Another example that will come up a lot is the equivalence relation on the integers that A is related to B if A minus B is divided by n for some n we decide beforehand. Call this tilde n for now. This division, I should clarify this, should be intuitive for the integers, but A divides B if there's some integer k such that ka equals b. It's the typical definition of divisibility. A is a factor, or n is a factor of a minus b. So, for instance, if we say n equals 3, then 1 is related to 4 because 1 minus 4 is negative 3, which is divisible by 3. 1 is related to 1 because 1 minus 1 is 0, which is divisible by 3. And 1 is not related to 3, for instance, because negative 2 is not divisible by 3. You might notice this is just mod 3, and we'll talk about that in a second. And this does happen to be useful because it is an equivalence relation. Clearly, everything is equivalent to itself because we get n divides 0 and everything divides 0. It's just a fact of like numbers. If n divides a minus b, then n also divides b minus a because this is just negative this, and if something divides k, it divides negative k as well. Lastly, say I'm running out of space. I'll just make a new page in a second. Say n divides a minus b and n divides b minus c, right? Well, if something divides k1 and it divides k2, it's safe to say it also divides k1 plus k2. So if we add these two, right, we get n divides a minus b plus b minus c, meaning n divides a minus c, meaning a is equivalent to c under n. So this is an equivalence relation. Let's talk about partitions for a second, and then I'll come back to this equivalence relation. Okay, partitions. So say we have set A. A partition of A is a collection. I say collection here. Collection means set when I say it. It's just sometimes good to distinguish because when I say collection, usually I'll mean a set of sets. It's still a set, that's fine. I just like to use the word collection to make it clear what I'm constructing. Subsets of A. Since we're dealing with finite sets, we're not dealing with finite sets. We'll be dealing with countable sets for the time being. But this does generalize. It's just for notation. So call each of these elements a sub I for some natural number I with the following properties. So first, no AI is empty. They're all non-empty. Okay. Secondly, they are pairwise disjoint. So AI intersection AJ for different I and J is always empty. So they don't overlap anywhere. And lastly, A1 union A2 and so on all the way is always equal to the whole set A. So we're just cutting A into pieces, right? This is the rules for cutting A into pieces where none of the pieces are empty. Okay, so we can actually find a correspondence between equivalence relations and partitions. So say we have an equivalence relation A, or tilde on A, right? We're going to define the equivalence class. Say we have an element A and A. The equivalence class of A is the set of all B in A such that A is equivalent to B. So all the things that are related to A. Notice I could write this B is equivalent to A. Since it's equivalence relation, it's symmetric, so it doesn't actually matter. Okay, so I claim, let's take all the equivalence class. We'll write the equivalence class of A by brackets A, given that tilde is known and clear. I might write like a subscript if it's unclear. So if, I should be careful, if B is an element of the equivalence class of A, I want to show that the equivalence class of B is in fact equal to the equivalence class of A. So let's do this. This is a quick little proof using all the properties. So this definition right here means that B is equivalent to A. Now we're going to do what's called a proof by double inclusion. So in order to show two sets of the same, say we want to show A equals B, it suffices to show that every element of B is in A and every element of A is in B. In other words, that A is a subset of B and that B is a subset of A. It's analogous to the fact that if you want to show two real numbers are the same, it suffices to show that A is less than or equal to B and that B is less than or equal to A. Subset is a very similar notion to less than or equal to. So from our definition here, we have B is equivalent to A, right? And then from our second thing here, we just take an arbitrary element of the equivalence class of B, call it K. So we're taking any element and we wish to show that it's in A, or in the equivalence class of A, in this guy. So from our definition, we know that K is equivalent to B because that's what it means to be in this equivalence class. And we know that B is equivalent to A, and so by transitivity, it follows that K is equivalent to A, and therefore K is in the equivalence class of A. And I could show the other inclusion, but it's literally the exact same thing. All you need to do for that is you actually first need to flip this to get that A tilde B. And then it follows that if K tilde A, then K tilde B, like this, right? Notice here, though, for this first part, I didn't actually use symmetry at all. I did need to use symmetry here. Okay, so the last property that's nice about equivalence relations is this always holds, and this always holds, and every equivalence class is always non-empty. Because A is always in its own equivalence class, because by reflexivity A is always equivalent to A. So you might notice these properties tend to line up a decent amount with our notion of a partition. So what we do is we take all the equivalence classes of different elements of A under tilde. We don't allow repeats. So for instance, we would just consider these two as one equivalence class, the set itself, not what element it depends on. And we actually get that this is a partition, and I'll do a quick proof. If AI, well, I just proved that none of them were empty, so that's fine. If AI and intersects with AJ, and they're not equal to 0, well then all we do here is we take some element in the intersection by our assumption that it's not empty, right? And we get, say, let's take K in the intersection. So for our definition of the intersection, it follows that K is in AI, which we're defining as some equivalence class A, since we're using the partition of the equivalence classes. And this means that K is equivalent to A, right? Additionally, by our definition of the intersection, K is also in AJ, meaning that K is, let's say this is equal to, I don't know, B, right? This means that K is equivalent to B. We flip this to get B is equivalent to K, and then by transitivity, B is equivalent to A, meaning that B is in the equivalence class A. And from here, it follows that our equivalence class B, so AJ, is actually equal to our equivalence class AI, right? So that they're actually the same set, so that our original assumption that I is not equal to J is false. Lastly, the reason they union to the whole set is we just need to show that if for any arbitrary A in the set A, that it follows that A is in some equivalence class K. But this is clear because A is in its own equivalence class. So every element is in some equivalence class. And that's it. The point is that every equivalence class, every equivalence relation gives us some way to break up a set into a bunch of equivalence classes, which form a partition. Okay, so before we get on to group theory, I have one more object to construct, which is the integers mod n, which I sort of hinted at earlier, but let me just hang on, check the chat. Let's make sure I'm not missing anything. Okay, cool. Oh, wow, a lot of people here. Okay. All right, back to this. Okay, so let's define the integers mod n. So by n, I'm going to fix, we're going to fix some n that is an integer, and for just nice notation, we're going to say n is greater than 0. So 1, 2, 3, 4, 5, etc. We're going to define the integers mod n. I'm going to make a new page for this. Okay. So we fix n in the integers with n greater than 0. And we're going to define an equivalence relation as earlier. I'm not going to prove it's an equivalence relation because I already did. By A is equivalent to B means n divides A minus B. Right? Then what I'm going to do to construct a new set is I'm going to take all of the equivalence classes. So what we did earlier, right? So here, let's say n equals 3 again. We're going to get our equivalence classes are going to be 0, -3, -6, and so on back here, and then 3, 6, right? Because 0 is equivalent to 3, 3 is equivalent to 6, etc. We're also going to get 1, and then -2, -5, and then 4, 7, that's a 2, and so on. And then our last equivalence class will be 2, -1, and so on, and then 5, and so on. And so it should be clear how these fit together to form a partition, right? There's no overlap between them, and every integer is in exactly one of them. And obviously, they're all non-empty. This is a partition because it's the equivalence classes of an equivalence relation. Okay, so this is fine. We have a set now, and it's useful. I should mention it. The set we're considering is this set, the set of all three of these. In general, there are n many of them, which I won't prove, but I think it's not too bad. You just show that there's zeros in one of them, ones in one of them, and all the way up to n minus 1 is in one of them, and those are all distinct. So we want to have a better notation for these sets, right? It's cumbersome to write this down every time. So we're going to write down a notation. Why do I keep doing that? What am I even doing? A notation 0 bar, or any number bar. I'll even just generalize it. I'll say j bar for an integer j is the equivalence class containing j, right? So just as our example, this top one up here could be called 0 bar. It also could be called 9 bar or -3 bar. This one's like 4 bar or 1 bar. You get the idea. So this is our better notation. And of course, this isn't, well, here's a little throwback to earlier. If we have the map from the integers to this set, I'm going to call it z mod nz. This guy, you've probably seen this notation before. This function that takes any integer I to its equivalence class I, which is equal to I bar by our notation. This clearly isn't injective because 9 and 0 go to the same thing. But it is surjective, obviously. Okay, just an aside about injectivity, surjectivity. Okay, so I want to just define on this addition. And this is sort of a prefigure to group theory, you'll see. So say we have two of these equivalence classes, called them k bar and m bar. I want to be able to get one of the equivalence classes back by adding k plus m, k bar plus m bar. The intuitive way to do this is to take k, the number, not the equivalence class, and m, the number, not the equivalence class, and take their representative. And this is exactly what we do. But we have to be careful because k and m aren't just one number. They could be any of the numbers in here. So what we have to be careful with is we have to be careful that we never get dependency on our choice of representative. These are called representatives. For instance, I don't want it to be that if I add 1 and 0 this way, I get a different result than if I add 4 and 3, because those should give the same results. We want this value to be independent of these values, as long as they give the same. As long as k bar and m bar are the same, we don't want it to depend on which representative we choose. But in this case, that's actually not a problem, and I can prove this really quickly. Let's say that we have k is in, let's just say we're adding k and m, right? So let's say that L is some other element in k bar. K bar, my bad, I should use better notation. Nope, that's not what I meant to do. Say L is some element in k bar, and P is some element in m bar, and any arbitrary element, right? Any other choice of representative. Then we wish to just show that L plus P bar is equal to K plus M bar. So this is the set of all, by our equivalence relation, this first one is the set of all A, such that L plus P minus A is divided by N. And this one is the set of all A, such that N divides L plus, or not L, K plus M minus A. We wish to show these same sets. Again, we do this by double inclusion. I'm just going to show one inclusion. It should be obvious that the other one will proceed exactly the same way. Okay, so let's say that this is true for some A. We're fixing some arbitrary A, right? Such that N divides L plus P minus A. Well, we know that N also divides K minus L. Is that right? No, sorry. Yeah, K minus L. Yeah. Because L is in the equivalence class of K. And we also know that N divides M minus P, right? So if we take this equation and we add to it, we're going to add to this right side, we're going to add K minus L plus M minus P. And it should be intuitive that this doesn't change whether N divides it or not, because we're adding two things that N already divides. If we add something that N divides, it doesn't change the divisibility of this by N. So when we do this, of course, the n's cancel out, the l's cancel out, the p's cancel out, and we get that n divides k plus m minus a, right? And of course the other inclusion will go exactly the same way. This means, of course, that a is n. And actually, I don't even need to do the other direction. I don't even need to skip it. Notice that these are different equivalence classes. So since a single element that's in L plus P bar is in K plus M bar, it follows that they're the same by our definition of our partition. If one of them was a subset of the other, or even if they have one element in common, they are the same thing. Because otherwise it would violate one of the axioms of that. I won't define multiplication here on Z mod NZ. I'll leave it as an exercise. It is very much the same. You just you want to define it this way just by replacing times plus with times, and the math then just comes down to showing that this is again invariant of which representatives we choose. Okay, so that was a bit of a precursor to group theory. Let's get on to group theory now, but I'm going to check, make sure. Sure. Okay, group theory. So what is a group? We have many examples of groups, and I'll give the I'll just go ahead and give the definition. I won't stall, but I will give a bunch of examples to give the definition. So first we need to define a binary operation. So we have a set G for group. A binary operation on not what I meant to do, on G. We're going to consider it as a function from G, we'll call it times, from G times G, this is the Cartesian product from earlier, it's the set of all tuples with elements in G, to G itself. So what this means is that we take in times of some elements G1 and G2, and this spits out another element, G3. G3 may be equal to G2, it might be equal to G1, it might be neither. Point is, we have a way of taking two elements in some order and getting another element. The order does matter here. So we'll immediately become less formal and call this output right here G1 times G2, using whatever symbol we're using for our binary operation. Generally, we'll use either times or we'll use G1, G2, just putting them next to each other, which both should be familiar. So what are some properties of binary operations we might want? Because as we have it right now, it's kind of a mess. It's any function. We can have basically anything that takes in two elements and gives out another element according to a rule. So we want a few main properties that we might want. Let's consider them. One is commutativity, and I'll talk about which one of these we actually need in a minute. So times is commutative, and this should be familiar from properties of the real numbers. If A times B is always equal to B times A, no matter what A and B we choose. This should be familiar. Associativity, again, familiar from the reals. I'm gonna I'm not gonna write the whole line because it's cumbersome. A times B times C is always equal to A times B times C. So I can't just write the product, without this I can't write the product A times B times C, because we only have a way of taking two elements. We don't have a way of doing three elements at a time. Once this is true, we have a way of doing three elements at a time, because when I write this, you can get it by just doing it one multiplication at a time, and you'll always get the same result. But this is why, for instance, writing down the notation, well, I'll give an example of a non-associative binary operation that should be familiar. Minus isn't on the integers, right? This is why writing down this is bad notation, because it's unclear if you mean this or this, because they're different things. But if suddenly these are pluses, it doesn't matter, because no matter which one you mean, it's all the same. Okay, 3, we might want some identity. So this is an element 1 that we're deciding in G, such that 1 times A, no matter which A we choose, is always A. And also, A times 1 is always A. So 1 doesn't change anything that it multiplies by. So this is, obviously, if you're using multiplication, it's analogous to the notion of 1 in the rationals or the reals or the integers. If you're dealing with addition, it's 0. Lastly, inverses. For any element A in G, we might want there to be some A inverse in G, with the property that A times A inverse is always equal to A inverse times A is always equal to 1. So again, this should be familiar with the reals. If we're doing multiplication, the inverse of A is 1 over A. If we're dealing with subtraction, it's negative a. Generally with groups, whenever we're not working in a specific group, we're working in abstract groups, we deal with multiplicative notation, so we'll write a to -1 instead of negative a. Mostly because, well, let me just give a definition of a group, and then I'll explain why. G, along with a binary operation on G, x, or times, is a group if times is 2, 3, and 4. So it follows these axioms. Not commutativity, importantly, but it follows these axioms. So it's associative, it has an identity, and there are always inverses. Commutativity would be nice. It is a nice thing to have. However, it turns out that a lot of really useful examples of groups, most of group theory, most of the important parts of group theory, deal with groups that are not commutative. Not commutative groups, this is just a piece of terminology, are called abelian. Commutative groups, I don't know, I might have misspoken. Commutative groups are called abelian, and correspondingly, non-commutative groups are called non-abelian. Most of the useful groups that we always deal with are non-abelian, but plenty of them are abelian, and the abelian groups have a ton of really nice properties, as you would expect. In fact, they're so nice, they're so nice, this is just an aside, we know, well, in a certain sense, we know a lot of the abelian groups. We know not even just the finite ones, but we know a lot of the infinite ones too, by classification. We don't know nearly as much about non-abelian groups because of just the sheer amount of structure you get from abelianness. Okay, so I should give a few examples of groups, just over here in the margins. The integers under addition are a group. You can just check these yourself. The rationals under addition are also a group. The rationals under multiplication are not a group, because, notice here, this needs to hold for all elements in G. And notice there is no multiplicative inverse for 0. We would write 1 over 0, it's a problem, right? However, this is an easy problem to fix. If you remember the complement from earlier, we just remove 0 from the set, and this is now a group. In fact, if I use this notation to mean the strictly positive rationals under multiplication, this is still a group. Because if you multiply two positive numbers, you get a positive number. If you take the inverse of a positive number, you get a positive number. Of course, this... I need to draw the cues. This... What? Please. I don't know what button I'm pressing. This, however, is not a group under addition, because obviously we can't take the additive inverse of a number and still have it, in general, be positive. Also, keep in mind, we've just tried this as strictly positive, we're also missing 0. The reals, just like the rationals, are a group under addition, and if you remove 0, they're a group under multiplication. These are sort of the typical examples, but smaller examples. Our group earlier, Z mod NZ, for any n, is also a group under addition. I won't prove this right now, but you can sort of take it from the definition. Basically, all of the properties you would ever want follow from the properties of the integers that we already have. Because if we go back to here, our properties of Z mod MZ were just taken from the integers. We're adding integers here. So all of the properties follow nicely. Right. So these are sort of some typical examples, and I'll construct a lot more as we go. What was up next? Let me check my notes. Yes, okay. I'm gonna give another group. I've given only so far abelian groups. Let me give a nice example of a non-abelian group that will be very familiar to cubers, hopefully. I'll give another more pertinent example later on. But there's this group D sub 2n, which I will construct later. But I'm just going to give it intuition for now. And actually, I'll just construct D8 because I think that's better. D8 is the symmetries of a square, including reflections, right? So all ways of rotating and reflecting this square, and any compositions of those things too. It should be clear that this is a group, because if we do some symmetry, so say we rotate it and then we reflect it, we can always undo that just by afterwards doing, I should mention, the multiplication here is doing the first thing and then doing the second thing. Or the other one. It doesn't matter which side you do first, but whichever one you want to do first. I generally do left to right. Point is, if we do something, we also have the symmetry that is just doing the things, the reverse of the things in the opposite order. So say we want to undo rotating this way and then flipping along this axis. Well, we just flip along this axis again and then rotate back this way. Whoops. And then rotate back this way. And that is the inverse. There's always an inverse. The identity element of this is the reflection that does, the symmetry that just does absolutely nothing. Everything just stays in place. Nothing moves. That's the identity. And associativity you can check by yourself, but it does hold. A property of this is, say we have, and I'll talk more about this group later because it's kind of important. It's a good example for a lot of things. Say we have S is a reflection along this axis. We're representing that by a letter. And then R is the rotation that goes this way at 90 degrees, right? So RS, for instance, we go left to right because that's what I'm used to. We rotate everything this way, and then we flip it across this axis. So if we track the coordinates, we write coordinates like this, 1, 2, 3, 4. Then, well, first 1 gets sent to 2. I'll just write up here. 1 gets sent to 2, 2 gets sent to 3. 3 gets sent to where 4 was, and 4 gets sent to where 1 was, right? And then they get flipped. So now, in the final state, we have 4 here, 1 here, and 3 here, and 2 here, right? So 4, 1, 3, 2. This is RS, is this state. I'll write it again here. 4, 1, 3, 2. SR, we're doing things in the other order. Well, let's see. 1 goes to 2, right? So this is 1 now, and this is 2. This is a bit cluttered, I apologize. And then 4 goes to 3, so this is 4, this is 3. And if we then rotate, well, 2 goes over to where 1 was. So 2 is now here. 1 goes over to where 4 was, so 1's here. And then 4 is now here, and 3 is here. Okay, so these are the same elements multiplied, but notice the vertices here are not the same as the vertices here. They're very different, in fact. Well, they're not so different. You can actually notice they're off by 180-degree rotation, which we'll get into later. So the point is that this is non-abelian group because we can multiply these two elements one way, get one result, and multiply them another way, get another result. Okay, what was next? Yes, okay, let's give some... one more way to define a group is by a multiplication table, and this is really only worth it for small groups. So what we do, say we have a group of, I'm going to define a new group by just giving a multiplication table. I think I've had this on the screen for long enough that it should be fine. Okay, so say we have a group. Our set for the group is 1, A, B, and C. Just 4 elements. This one is suggestively called 1 because we will make it the inverse, but for now it's just 1. What we're going to do is we're going to make a 4x4 grid with some labels up here and over here. This is just a way to define a binary operation. Typically, we will construct a binary operation in a number of ways. One of the popular ways is to construct it from another binary operation. That's what we did with the Z mod MZ. Notice when we did this, we sort of just piggybacked off of our already known definition of integer addition. Another way is through relations, which we'll get into later. This is sort of the most brute force way, which is just writing a table. So we write a table here, and then every row is the product. Every element of the table is the product of the vertical, the row its column element it's in, times the row element it's in. So this right here would be the product AB. But AB, we don't know what AB is, so we're just going to say what AB is. Let's say AB is defined as C. BA is also defined as C. C1 is defined as C, clearly. C1 is also defined as C. Let's define AA as 1. Let's define BB as 1, and CC as 1. Let's define AC as B, and also, sorry, this is slanted, I just realized that. AC is going to be B over here as well. And then BC is A, CB is A. I'm just defining it here. This isn't coming from anything, I'm just defining it. This is B, this is B, this is A, and this is also 1. So we just defined a binary operation. And now we could check from this that it's associative, but of course, if we wanted to just brute force check it was associative without a rule, we would have to check, well, we'd have to check 64 possibilities, and that would suck. So even just writing out these tables, this is 4 elements, which is a really small group. Once you get to 16 elements, it's not worth it anymore, obviously, because that's 256 tiles. That's not worth it at all. But it should be clear from our definition that a group is abelian if its table, I think this is called a Cayley table, I've always heard it called a multiplication table, is symmetric around the diagonal axis here, right? That every element here is always equal to the element here. Because that element there represents the product AB, then the element across the axis represents BA. And if these are always equal, then we have an abelian group. I would, as an example, draw out the table for D8, but it would have 64 entries. I don't think it's worth the time. This is a new group. We call it the Klein 4 group, or V4. We'll find different notation for it later. But we just define a new group through this. Again, we have to check inverses, identity. Identity is very easy to check. It's obviously 1. Inverses aren't too bad. It holds that every element is its own inverse, which is fine. And then associativity would be a pain. But we have a new group that we constructed through this table. And like I said, this is only useful in very small cases. Okay, let's go over some basic theorems about groups. I'll just erase this because I don't think it's... Okay, so I'm going to give a few theorems. First, I'm going to say the identity is unique. So let's say we have E and E prime, both identities. If we go back to here, just to remember, an identity is something that when you multiply it by every element, you always get the element back, no matter which side you're on. And note, the identity, I was sort of skipped notation here, but what I meant by this is that there is some identity. We don't clarify there's only one, but I can show you that there's only one. It's very easy, in fact. Say we have E, their first identity. Well, this is clearly equal to E times E prime by our definition of the identity, right? If we multiply E by an identity, it stays the same. But, of course, if we multiply E prime by an identity, which is also what we're doing here, we're getting E prime again. And so it follows that E equals E prime, so they're the same. So identities are always unique. Let's talk about the uniqueness of inverses, right? Let's say A inverse and what's a better notation? Let's say B and C are both inverses for A. So it follows that AB equals 1, right? But also AC equals 1. So let me be careful here. If we multiply both sides of this equation by C on the left, we are not changing the value because we're just passing this. We're multiplying this by C and multiplying this by C. And since they're equal, they should still give us something that's equal. When we do that, we get C. Oh, I should also mention, we also have that BA equals 1 and that CA equals 1 by the definition of an inverse. So we get that CAB equals C. We multiplied both on the left by C. You do have to be careful. If I have x equals y, it does not always hold that xc equals cy. Because here we multiply on the right, here we multiply on the left, you have to be careful. This does, of course, hold if it's an abelian group, but not always. So be careful that you're only left or only right multiplying. And of course, if I have like xy equals z, I very much cannot do xcy equals cz or something. Okay, so we have CAB equals C. By this rule, we have that 1b equals C. And of course, by the identity, we have that b equals C. So they are the same element. Another one is we're going to show that A inverse inverse. The inverse of A's inverse is equal to A. By the way, we can uniquely write this now. This notation doesn't just mean an inverse of A, it means the inverse of A, as we just proved they're unique. So to do this, we just multiply A inverse inverse by A inverse, right? Now, we have, by the definition of our inverse, that this is going to be equal to 1. However, if we multiply both sides by A inverse inverse A inverse A equals A, right? And notice this is equal to 1, so we get A inverse inverse equals A. Okay. Another good theorem. Inverses only have to be one-sided to be two-sided. So, yeah, let me just prove this. What I mean by that is that, say AB is 1, then B is equal to the inverse of A. Notice that for inverses, we also need BA equals 1, right? But it turns out that we can take AB equals 1 and get BA equals 1 without too much trouble. We take AB equals 1, right? There's some inverse of B. We right multiply by it. So we get A, B inverse equals B inverse. This cancels out, we get A equals B inverse. Then we left multiply by B, so we get BA equals B inverse. And then this right side cancels out, we get BA also equals 1. So that B equals A inverse. Okay, one last theorem, which is also a very easy one using what we just proved. We claim that whoops, that's way too zoomed in. We claim that if we multiply A b and then take the inverse of that, this is the same as taking the inverse of b and multiplying it by a inverse. So this, notice that the order got flipped here, and this does make sense once we multiply it out. We want to show that ab times we know this is true. Well, hang on. I just need to, it suffices to show that if I multiply these two things, I get 1. Because as we just showed, if this is a one-sided inverse for AB, it's also an inverse. It's a full inverse. And so, of course, by associativity, this is equal to the general product AB, B inverse, A inverse. This becomes 1. We have A1, A inverse. This cancels out. We get AA inverse, which is obviously equal to 1. So that this is equal to 1, and therefore this is true. Okay, I think that's it for introductory theorems. I don't think I'm missing anything important. Oh, the cancellation laws. Yes, this is obvious, but if we have VA equals VB, then it follows that A equals B. And this is clear just by left multiplying by the inverse of V. This is why, another intuitive reason why the reals under just multiplication without removing 0 is not a group, because of course 0 times 1 equals 0 times 2. The cancellation laws don't hold here because 0 doesn't have an inverse. But they do hold in a group because that's not a group. We need an inverse for every element. Okay, and I should mention, obviously this is also true, then A equals B, or B equals A. Again, just by right multiplication by the inverse. Okay, let's talk about a classic example of group, and I'm going to try to do this. Actually, you know what? Hang on. What's up next? Yes. Okay. Give me just a second. I gotta find something. Okay, I'm gonna give a classic example of a group. Let's change windows. Okay. So we got this guy, right? Let me actually just have a cube. Is that somewhere? Well, sure. No, that's the 1 by 1 by 1. This guy. Oh. Okay. Well, you know, just pretend this is a cube. We don't care about the Rubik's Cube part right now. I'm just going to deal with the cube part. I don't know. I don't have a cube anywhere here.
Sorry.
No, it's all good. Just like ignore the lines here. So we can talk about the rotations of this cube as a group. And let's think about how we do that. If we start from a given state, let's pick a state. I'm going to pick yellow on bottom, green on front, because this is how I scramble. So this is our starting state, right? The elements of our group are rotations from here. So, for instance, one element might be doing this, where we just rotate up like that. One element might be doing this, where we rotate to the right. It's kind of hard to do, but another element might be that weird rotation where we like flip around a vertex. If you're holding a cube, it should be easy to do. I'm not sure exactly how to do it by panning here, but there are many rotations is the point. And we can also think about every different way of holding the cube as a rotation, because how do I phrase this? There is one rotation that's okay, let me think about this. We need to be careful. When we multiply some rotations that are different rotations, we might get the same element. So sort of a nice example is if I rotate twice this way, right? And then twice this way, and then twice this, I don't know how to rotate, twice that. It's hard to do in HSC too.
One thing you can do is hold numbers 1 and 2 on your keyboard and then click on the gizmo. That way you can do rotations.
Oh, so true. That's so true. That's a good example. Okay, sure. Yeah. Yeah. So if I start from our starting state, which is here, if I rotate twice this way, and then twice this way, and then twice this way, I'm back to where we started. Even though none of those rotations were inverses. There's no nice way to cancel those out, right? I didn't undo anything, but I did 3 different turns, and I got back to the original one. So we consider, say that first turn, let's go by Rubik's Cube notation, say this turn is x, x2, and this turn is, what is this? This is y2, and this is z2. It follows that x squared, y squared, z squared, x2, y2, z2 is equal to 1. It's equal to the identity rotation because we didn't move anything in the end. Even though we did do a rotation, we're considering it the identity. And it should be clear in this definition that if I rotate this way and then back this way, that the inverse of x is x prime, right? And the inverse of z is z prime. I might have done z prime z there. You get the idea. Associativity is, you know, again, it's annoying to check, but it's not hard. Point is, what is the size of this group? How many elements does it have? Well, the Rubik's Cube as a specific example is really nice here. because it has it has no chiral, like there's no symmetry of the colors, right? Every coloring of the cube, okay, how do I phrase this? We can uniquely determine which rotation we've done by where the different faces of the cube are, because we've colored them, right? So, for instance, if I just look at the cube, if I do a bunch of random rotations, I look at the cube and I say, well, now white's on the right side and green's on the top. I know which rotation I did. I did the rotation I did this rotation, right? So every rotation corresponds to some permutation of the colors. Now, we can just think about it this way. How many orientations of the colors are there? It should be easy to see that to determine where the colors are, I only need to know the color on the front and the color on the bottom, right? Because the color on the bottom will tell me the color on the top, the color on the front will tell me the color on the back, because the opposite colors never switch. They're always still opposite colors. And then because it is a physical thing, we could theoretically have that orange and red are swapped here, but that actually can't happen just because you can't swap two faces. It's not geometrically possible. So the point is, there are 6 choices of which is our front face, and 4 choices of which is our side face, because obviously it can't be blue in this case, giving a total of 24 elements. Every element is uniquely determined by which is on the front and which is on the top, given that we've chosen an initial state. It should also be clear this is obviously a non-abelian group, because if I rotate x and then I rotate z, it is not the same as rotating z and then rotating x. Those are different elements. But some elements commute. Abelian groups often have some elements, and they always have some elements commuting, but they often have some decent amount of the elements that actually commute. So I believe, if I'm not dumb here, these elements commute, I believe. Because look, we got green on front, white on top. Whereas if I do this first, and then that, I still have green on front, white on top. So those 2 elements, x2 and z2, or x2 and y2, those commute. But not all elements commute. Okay. Back to the drawing board here. That's a good example of a, whoops, that's not the middle. Okay, somehow Discord doesn't hang on. It's not liking my, it doesn't see my GIMP anymore? Okay. Sure, I guess. You can just see my whole screen. Can you see GIMP? Someone confirm?
Yeah, I see it.
Okay, cool. So I'm going to do one more thing today, and then I'm going to end it there. And that's I'm going to talk about generators and relations. And this is going to be a bit loose because the strict definition is very complicated. New page. Although actually, I guess this page I can just erase. This was one theorem. Okay, so generators and relations are a way of defining a group without defining it as a based on another group, and also without drawing a whole table. So we're going to define generators and relations. They're going to look like this. They're going to look like some number of elements, and then a bar, and then some equations. So I'll give the typical example here. I'll explain what this looks like. So what these mean is that our elements of the group are all ways of multiplying R and S, right? So R, S, R, 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 S, R, and their inverses. So R inverse, S, R, S inverse, R inverse. This would be an element of our group. All finite strings of length made up of these elements and their inverses, right? If we just have these together, and our only rule is that R inverse is 1 and S inverse is 1. If that's our only rule, we get something called the free group, which is really big, right? So like RS, R, S, R is a different element as RS, RRS. These are different, and all elements are different unless one of them, unless they happen to be the same string of things. And our only rule here is that when we multiply things, we put them end to end. So RS, RR, S, RR, we multiply them. And our only other rule is that if we have R and R inverse next to each other, we cancel them out. Free groups are useful in some cases, but they're generally too big to work with because we have no structure, almost no structure. So what we have here is we have rules that we're allowed to use to simplify. So if we have a string here, let's take a string R, 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 S, S, R, right? Well, we look at our rules. We can write this as R cubed S squared R. And we notice that according to our rules we defined here, S squared is equal to 1. So we get R cubed 1R. And of course, this is equal to R cubed R. which is of course equal to r to the fourth. And we've also seen that r to the fourth is also equal to 1. So this string simplifies down to 1, according to our rules that we defined to give ourselves a bit more structure. We have another rule here that's very useful. This is what's called a what's it called again? Commutation rule. Basically, if we have an r on one side of S, we want to get to the other side. If this were an abelian group, or if these two elements commuted, it would look like this. We're dealing with a non-abelian group here. So we notice that RS is not equal to SR. Okay, so let's look at simplifying some other strings. If we look at RSR, right? Well, this is equal to SR inverse. So this is SR inverse R, which is equal to S, right? So this gives us a way to simplify down strings. The first thing I'm going to claim is that there are 8 elements in this group, which is interesting. If we take the free group, there are countably infinitely many elements, if you know what that means. There are infinitely many elements of this free group. There are infinitely many strings. But I claim that according to just our 2 rules here, they can all be simplified down to just 8 strings. And the strings are as follows. Whoops, I have no idea what I just did. I probably zoomed out in a weird way. Yeah, okay, we're fine. Okay. So I'm going to list the 8 elements, and then I'll show that everything is equivalent to them. Nope, not what I wanted. Please? Oh, okay, we're back. So our 8 elements are the identity, r squared, r cubed, and s, sr, sr squared, and sr cubed. Okay, so a note on why these rules aren't enough. If I just had these rules, I would still get countably infinitely many strings because RS and RSRS and RSRSRS, these would all be unique elements, which would be a problem for us. This rule lets us simplify these long chains down to one of these 8 elements. So that's why commutation rules are really useful. Okay, so let's look at this. Say we have a string that is RSR, I'll put it this way, it's r to the k, s to the, r to the a1, s to the b1, r to the a2, s to the b2, right? I'm going to give you a loose proof here. If this keeps going, every r that is on the left side of an s, so here, first thing we should do, every s to the b2, to the bn, either becomes s to the 1, which is s, or it becomes s to the 0, which is 1. Because s squared is 1, right? So we're efficiently taking the exponents mod 2, right? If it's s to the 4th, this simplifies to 0 or to 1. If this is s to the 5th, then it simplifies to s. So that's the first thing we do. The second thing we do is we do that with r as well. Every element r to the an simplifies down to either 1, r squared, or r cubed. Again, just by modular arithmetic. Okay. Next, every r to the n, r to the ai, let's say, that is left of an s, we move it to the right of that s by using this commutator rule. It should be clear by just repeatedly applying a rule that r to the a times s is s times r to the negative a, r to the negative a being r to the a inverse, which is also equal to r inverse to the a. So we can effectively move all of the r's to the right of the s's. And by doing this a bunch of times, we will collect all the s's at the left and all the r's on the right. The r's on the right will have some power. It's going to be really complicated because it's all of the powers, some of them taken negative, some of them taken negative multiple times. It's going to be a complicated power. But the point is that every string is simplified down to s to the k, I'll just do s to the a times r to the b, right? And then by just doing our process again, we get s to the let's call it c, r to the d, where c is 0 or 1, and r is 0, 1, 2, or 3. So we've simplified it down to one of these 8 cases, right? By using both of our rules here. Without either of these rules, our group would be, if we remove one of these rules, our group becomes infinite. We get a different group based on that. I can generalize this notion. Notice I said r to the 4th here. Oh, and if it's not, sorry, I should before I move on, I should mention this. This is the same square symmetry group from earlier. If we consider again from earlier r, let's fix an axis. Let's say it's this axis. R is the rotation, let's say clockwise. Well, I did counterclockwise earlier. I'll just stick with that. Clockwise by 90 degrees, right? This is r. And s is the flip around this. We can check that our rules hold. right? So first, obviously, if we rotate 90 degrees 4 times, that's the identity. We've done nothing. If we flip twice, we've also done nothing. And you can check yourself, but if you, well, I'll do the work. Say our axes are 1, 2, 3, 4, as earlier. If we first rotate, right? So we're now at 4, 1, 2, 3, and then we flip. So then we get to 1 or 4, 1, 3, 2, right? This is the same as if we flipped first. So we got 2, 1, 4, 3, and then we rotated the other way, our inverse, which is rotating 90 degrees clockwise. In which case we get 1, 2, 3, 4. So these are the same, right? This up here corresponds to RS, and this down here corresponds to SR inverse. So this shows that our rules up here hold. And so this is the same group. And obviously, as you can check, this has 8 elements. Mostly you can see this geometrically as 8 elements because 1, 3 as opposite pairs are always preserved, and so are 2, 4. These are always opposite. And so we can place 1, 3 in any of the 4 slots. 1 goes in any of the 4 slots, 3 goes opposite it, and then the other pair, 2 and 4, only has 2 places to go. And it turns out all of those are possible. I can generalize this. I should go back to what we did here to make a note. I think it's still there. Oh, I erased it. That's a shame. We can generalize this notion of the symmetries of a square to the symmetries of an n-gon, a regular n-gon, by writing down this notation. D sub 2n, for some n, we were defining a group for an integer n. Same thing, it's generated by the rotation and the reflection. And the only thing we change, it's going to have all the same rules. Whoops, not one. It's going to have all the same rules except that the rotation is taken to the nth power to become 1 instead of just the 4th power. And so if we look at a hexagon, the same thing, we need to pick a daxis or rotation that preserves vertices, but that's not hard. In fact, for the geometric intuition, I'm going to try really hard to draw a regular pentagon. That's close enough. I said hexagon, I think, but I meant pentagon. If we draw a pentagon and we take an axis, let's always say it's the vertical axis here. I missed. You can check yourself that this rule always holds, that RS equals SR inverse. The only thing, and of course the reflection still has order too. You still have to flip it twice to get back to the inverse. The only thing that changes is that now if we rotate 4 times, that's not enough. We have to rotate 5 times to get back to the identity. And this defines a whole family of groups D sub 2n for any n greater than 0 in an integer, which is the symmetries of an n-gon. We could similarly use generators and relations to define the cube rotation group. I don't remember them, but they do exist. And you could do this. You have to be careful with generators and relations. If I just write down some rules, that's not always enough. I need to write down enough rules that I've specified exactly what I'm talking about. So, for instance, let's say our rotations that generate are x, y, z. We know that x squared, y squared, z squared equals 1, because we showed that. This is not enough, though. This is just not enough information. This is still going to make an infinitely large group. But we can just keep adding more and more rules that we know are true of the cube until eventually we get enough to specify it. I forgot to look these up, but you can look them up yourself. They do exist. So basically, any group can be written down by its generators, these, and some set of relations. There is a rigorous foundation for doing this. It's just well beyond the scope of what I'm talking about, but it should be an intuitive idea. That is all I had slated for today. Oh, yes, the good one we need, yeah. Okay, did I have anything else to cover? Let me just double check. Yep, that's it for today. Any questions? Yeah, you can get the cube group with 2 generators, yeah. Okay. Well, that's it. I'm gonna end it here. But
Thank you. That was excellent.